Welcome to the third Excelero webinar of 2020. I'm very excited to say that this is our most popular webinar to date. And as such, we wanted to make sure that we give you guys the best value for your money, or should I say time. So today I have no less than 3 superstar speakers. I'm extremely excited to be able to announce Dr. Dimitrios Emmanoulopoulos, who is a lead data scientist, applied R&D at Barclays. Dr. Dimitrios has many years of hands-on AI, GPU, and NVMe storage experience. He's here to share his experience building a full hardware and software stack for financial AI use cases. Also with us is our own Sven Bronner. He is field CTO at Excelero, and prior to that, he was inventor of BGFS, probably well known to most of you. Sven will be sharing some exciting results from performance tests that he and his team just finished running on NVIDIA DGX servers, using Supermicro Big Twins with Mellanox networking, NVMesh, Elastic NVMe. The results were really awesome, mind-blowing to say. So very much looking forward to that. But of course, as it should be, we like to let ladies go first. Kicking it off today will be Jacci Cenci. And Jacci is an experienced senior marketing engineer at NVIDIA. She is a certified deep learning instructor who is also responsible for driving reference architecture development with Instructor partners. In preparing this webinar, I was super impressed with Jacci's wide storage knowledge and skills, so this will be very promising. Before I hand it over to Jacci, here is some logistics information. We want this webinar to be very interactive, and we would like to get as many questions from you guys as possible. And this is how this will work. So everybody but the panelists will be on mute, but at the bottom of your UI, you should see a Q&A button. Use the Q&A button to post as many relevant questions as you want, and we have a team of specialists that will be answering those questions live. The most interesting questions I will save for the end, and I will present those to any of our speakers. With that, I'm going to pass it over to Jacci.
Sure. Thank you, Tom. I want to begin by discussing the vital role in choosing the right storage, networking, and compute technology plays in balancing large-scale enterprise deployment environments for accelerating AI and predictive analytic workloads. I want to look at the system from a holistic perspective with all of you today. So let's begin by looking at some of the challenges that are affecting data science today and what requires solving to empower the data scientists. AI is already transforming the face of industries and various verticals, and deep learning and machine learning algorithms are helping to enable not only the data scientists, but the workforce and improving customers' experiences at the same time. Maximizing its potential, however, is limited by 3 things: manageability of data volume and velocity, slow CPU processing, and a complex end-to-end data management. I believe if we can solve these 3 things, we can get better insight that translates into higher business value. Today's organizations have access to vast amounts of data, and this data onslaught is growing exponentially. According to IDC and MarketWatch organizations, the storage industry will ship 42 zettabytes of capacity over the next 7 years. And by 2025, 49% of data will be stored in public cloud environments. Nearly 30% of the data generated will be in real time. There's so much data that it's next to impossible to process it all. And with the flood of incoming data, data sets are more massive than ever. And I'll be talking about that as I go through my presentation. That incoming data is inconsistent. Analysts estimate that 80 to 90% of the data in any organization is unstructured. They come from different sources, different periods, and different formats, and popular data science tools are in dozens of software repositories. Many of these are open source and revised frequently. It's very challenging for data scientists to find the right version that all works together. CPUs for processing data aren't just automatically getting significantly faster year after year either. GPUs, however, in contrast, can break down very complex problems into thousands or millions of separate tasks and work them out at once, performing much more work for every unit of energy than a CPU. NVIDIA delivers several critical benefits to organizations using data science. Because NVIDIA GPUs process data so much faster, it gives data scientists two unique advantages. First, it allows for faster time to insight, dramatically reducing how long it takes to extract meaningful content from a sea of data. And second, this speed allows for more iterating on a solution. This gives data scientists the ability to fine-tune their models and create more accurate predictions. NVIDIA integrates hardware and software, which not only allows for optimizations across the entire stack, but it simplifies setup for the user as well. Together with Excelero, we're testing and validating the power and performance that GPU accelerated storage, networking, and compute technologies offer as a complete integrated solution architecture. We're helping enterprise to implement artificial intelligence in their business and enabling them to break down these three significant challenges and create more adaptive processes. Together, we accelerate the data science workflow for every user and every organization, on-prem and in the cloud, making GPUs more accessible as we eliminate this enormous data problem. These are three critical business use cases. Choosing the right infrastructure can significantly increase the efficiency and accuracy of forecasting, for example, directly contributing to bottom line growth. Aiding data science efforts in identifying anomalies in data for fraud detection can rapidly save money for organizations and customers. And recommender systems connect consumers to a more personalized experience. With the combination of recursive neural networks and deep collaborative filtering technology, both short-term and long-term interests are integrated. The combination makes it easier for merchants to present the appropriate products to users on time. Each is an essential financial use case where accelerated data science makes a significant difference in end user satisfaction. Dr. Dimitrios Emmanoulopoulos, I hope I pronounced that correctly, from Barclays during our presentation today, will discuss commercial use cases in broader terms for you. There are many different areas of finance experimenting with AI algorithms to solve today's complex problems. Some of these examples here include anti-money laundering, ATMs, automated systems for credit scoring, and customer call routing. In several of these use cases, conversational AI and natural language processing have massive data sets containing thousands of conversations as well as labels and annotations for training digital assistants to determine users' preferences and intentions better. The ecosystem for data science built on CUDA-X AI is extensive. It spans open source, enterprise startups, and many other partners. The platform that you see here This approach allows for integration with NVIDIA accelerated data science from OEM partners, cloud partners, our storage partners, as you can see here with Excelero. I'd like to spend a few minutes describing just how shifting data off the CPU to the GPU with Excelero works. I/O acceleration to GPU is a force multiplier for computing once the whole data process pipeline shifts to GPU execution. As these AI and HPC data sets increase in size, the time for loading data for a given application begins to place a strain on the entire application's performance. So when considering end-to-end application performance, fast GPUs are costly and inefficient when I/O is slow. The CPU has historically controlled this process of loading data from storage to GPU processing. In the flow at the top here, as computation shifts from slower CPUs to faster GPUs, I/O becomes even more of a bottleneck to overall application performance. The data comes in from the storage and goes through a time-consuming CPU pre- and post-processing phase after offloading back to the storage server. But here at the bottom, the bottleneck is eliminated as massive amounts of data move directly from storage to the GPU, bypassing the CPU, which gives the data scientists the extra time needed to fine-tune their models and create more accurate predictions. Together, NVIDIA GPUDirect Storage plus Excelero, Remote Direct Drive Access, or RDDA, means the CPU is bypassed for accessing remote NVMe. We're helping businesses process data with reduced latency, making it much faster to extract meaningful information in real time. Let's dive a little deeper here with our GPU optimized systems with GPUDirect Storage. GPUDirect Storage is the newest addition to the GPUDirect family. In 2011, NVIDIA announced GPUDirect peer-to-peer to enable a direct memory access path between the memory of two GPUs. And in 2013, GPUDirect RDMA was announced, enabling network devices to access GPU memory directly, bypassing the CPU host. And last year, in 2019, we announced GPUDirect Storage. This allows direct memory access between GPU memory and storage, such as NVMe and NVMe over fabrics, thus avoiding a bounce buffer through the CPU. This direct path increases system bandwidth while decreasing latency and utilization load on both the CPU and the GPU. Some people would define a supercomputer as a machine that turns a compute-bound problem into an I/O-bound problem. GPUDirect Storage helps to relieve the I/O bottleneck of creating more efficient, large-scale balanced systems. It unifies storage with the GPU, and it takes all the GPU I/O and places it in the hands of the developer. And this eliminates extra copies of data and removes the tier of complexity and the I/O bandwidth bottleneck. In this case here, you see the GPU has higher I/O bandwidth than there's bandwidth to the CPU memory. GPUDirect is part of our Magnum I/O suite. Magnum I/O is NVIDIA's multi-GPU, multi-node networking and storage I/O optimization stack for simulation, data analytics, machine learning, deep learning, and visualization. I've talked to you about balancing, having a true holistic system. From a balancing perspective, Magnum I/O provides all the APIs that make network and I/O performance more efficient. providing a tuned and easy installable solution for all CUDA platforms. This optimized implementation for current and future platforms is available from the desktop to the cloud, whether data transfers are fine-grained and latency sensitive or coarse-grained and bandwidth sensitive for collectives. I spoke earlier about the problem with data set sizes no longer fitting into system memory and data I/O to the GPU growing to be the defining bottleneck with increased processing time. Pulling it all together here, we have the direct benefit of speeding up computation with GPUs instead of CPUs. We can enable a direct path with Magnum IO, GPUDirect Storage, and Excelero to reduce, if not alleviate, this bottleneck. Advances in I/O plus choosing the right system platform with CUDA architecture for massively parallel processing, NVLink and NVSwitch for high-speed connectivity between the GPU and CUDA-X AI unlocks the flexibility of our NVIDIA Tensor Core GPUs to address the end-to-end pipeline uniquely. CUDA-X AI, if you're wondering what that is, consists of more than a dozen specialized acceleration libraries that are free as individual downloads or through NVIDIA's GPU Cloud repository. We can speed up machine learning and data science workloads as much as 20x with these pillars of data science performance. For example, cutting 1 hour to 3 minutes faster processing time. To address these massive data sets, we need to right-size our DGX server platform as well. The NVIDIA DGX2, consisting of 16 Tesla V100s, contains a stock configuration of 30 terabytes of NVMe SSD memory and 1.5 terabytes of system memory. So when you couple with GPUDirect Storage and Excelero, we can offer fast memory access, increased bandwidth, lower latency, and potentially unlimited storage capacity. With these 16 GPUs and one OS for strong scaling and sharing of data, we can support a combination of scientific computing, data analytics, deep learning, machine learning, and visualization. We have 8 network interconnect cards for 100 gigabytes per second of network storage I/O and up to 16 drives for 50 gigabytes per second of storage I/O. And the PCI switches enable a direct connection from storage or network to the GPUs. NVIDIA provides an entire suite of GPU-accelerated data science platforms, meeting end-to-end data science requirements, including cloud service providers, high-end PCs for machine learning enthusiasts, enterprise desktops, and shared infrastructure for the entire data science team. It's been thoroughly tested and validated for maximum flexibility and maximum performance. So with that, I'm going to stop sharing, and I'm going to turn it over to Sven to continue discussing Accelero's Remote Direct Drive Access, RDDA, for accessing remote NVMe at speed of local internal NVMe for shared GPU storage.
All right, thank you so much, Jackie. Wonderful presentation as expected. Thanks again. And while Sven is getting ready, we decided to take a look at who's in the audience. So we put up a little poll here to get an understanding of whom in the audience has GPU infrastructure and what it looks like. So it would be awesome if you folks could answer this question. And as Sven gets ready, I'm super excited to hear his presentation here because Sven and his team, they did some wonderful benchmarking performance tests, and the results were incredible, and he's going to present it right here. All right, Sven, take it.
Okay, thank you, Tom, and thank you, Jackie. I guess one thing is clear to everyone by now, probably already before you joined this webinar, that the GPU workloads can be pretty demanding on the storage side. And that's for all the good reasons, of course, because NVIDIA is doing a great job at enabling very efficient computing on the GPUs, but this is also putting a lot of pressure on the storage system to make it provide all the storage at the right speed that the GPUs need. So let's take a closer look at what these typical GPU storage demands actually look like today, especially for deep learning. And the first thing we then hear almost every time is we need very high bandwidth for lots of small files. So that's, of course, for all the classic storage systems that have been designed for the spinning disks, that's a super tough problem that they try to address these days. But fortunately, back in 2014, when Excelero was founded, the company had a strong vision that there would pretty soon be the day when NVMe technology becomes really affordable for everyone and will be available to solve this problem. So welcome to the future now. NVMe storage is available to everyone and really affordable. And now it comes down to the right software to really make good use of all the NVMe storage. Which brings us to the other problem, low latency that we always hear, right? To keep these GPUs busy, they can do so much great parallel processing, multiple GPUs in parallel. You really need the low latency to keep feeding them and make sure that they are busy all the time. So you need the low latency with highly concurrent access. On the hardware side, again, NVMe is just the perfect technology to fulfill this. But the classic storage systems that were just not designed around this ultra low performance, they really have a hard time providing this performance. So what's the problem? The problem is you need to be able to scale the performance of the storage system and the capacity of the storage system independent of the GPUs typically. So that means you want to have it on external servers so that you can share the data with all the GPU servers in the system and scale both independently. So you need to be able to make this performance available over the network and still provide the low latency and the high IOPS and the high bandwidth all together. And the other thing is, of course, that when you start small, typically you're in the good position that your data set grows and grows. So you need to have a strategy that allows you to add more servers at any time, not only to increase the capacity, but also to increase the performance. So let's look at how NVMesh solves this problem. What we see here at the bottom are standard NVMe servers. That means it's commodity off-the-shelf hardware with any kind of NVMe drive. And what Excelero's NVMesh as a pure software on top of that does is we call this an elastic pool of NVMe, meaning we have an abstraction layer on top of the individual NVMe drives through which we can create logical volumes. Logical volume means you can have the capacity of all the NVMe drives in the system or a fraction of the NVMe drives, whatever fits for your workload inside a single logical and protected large volume that appears to your GPU servers like a single, I would call it ultra fast and ultra large internal NVMe drive. And now let's look at one of the magics behind NVMesh that was already mentioned before by Jackie. This is what we call RDDA for remote drive access. This is really the key of making the performance available over the network. And what we see here on the left-hand side is a GPU server. So this can be a DGX 1, 2, or whatever GPU server makes sense for you. On the right-hand side, we see a separate server, commodity server, with a fast network interface and an NVMe drive. And now the GPU server wants to access that NVMe drive at maximum performance. Here we're only seeing a single NVMe drive in the example, but of course, typically your servers will have multiple NVMe drives per server. So what's the fastest possible way to do this? of course, the request needs to go over the network, arrives at the network card of the server. And now comes the very important aspect. If we would need to wake up a process here on the server side on the CPU, we would immediately limit the number of IOPS and put a lot of extra latency on top of the access to the NVMe drive. So what Excelero's RDDA does on commodity hardware, again, just by running our software on the standard server, it enables the standard network card to access the NVMe drive directly by completely bypassing the CPU. That's how we can really make all the performance of the NVMe drive available to the GPU client here as if it would be an internal drive inside the GPU server. And of course, this access can be shared with any number of GPU servers. So this is, of course, only one of the important aspects of NVMesh. Why am I emphasizing especially this aspect? Because it goes so nicely together with GPUDirect Storage that Jacci also already mentioned. But just to have it in mind again, how does the data flow go without GPUDirect Storage, no matter whether it's an internal NVMe drive or remote storage? It goes through the PCI switch, through the CPU, adding some extra latency, then to the system memory, and then all the way back from the system memory, it gets transferred to the GPU. So this will, of course, be much better with the availability of GPUDirect Storage, because as you can see here, on the one hand, the pipe is much bigger if we go this way directly, and we don't have the extra round trip through the CPU and the system memory, because the network card or the internal NVMe drive is enabled to communicate directly with the GPU. And that's why NVIDIA and Excelero's RDDA are such a great match, because we have the same vision of what the future needs to look like and how high performance storage needs to look like by enabling direct device-to-device communication. So how would a deployment model for this look like? Here are just some very simple examples. On the left-hand side is what we call a simple storage expansion, meaning you have your GPU server, but you want to be able to have more performance or more capacity than whatever fits inside your GPU server. So you just take a single standard commodity server with an arbitrary number of NVMe drives, run NVMesh here and on the DGX, and then all the capacity is available, protected to the GPU server. Very simple. The other alternative is that this can, of course, scale out to an arbitrary number of GPU servers or storage servers. The fact that I'm using 4 for each here does not mean anything. It can be more servers or it can be more storage boxes, of course. The important thing is, on such an architecture, you would typically run a parallel file system if you go the classic approach. But the nice thing that I'll show on the next slides in the benchmarks is there's a very good motivation to not even use a parallel file system, to really have the full performance of all the NVMe drives available to your GPU servers. And still with Excelero's NVMesh, as the access here is shared, we can have a single large volume across all the servers. It's still a single namespace, even without a parallel file system. So enough of the theory. Let's get to some actual benchmarks. If you're familiar with GPU storage systems, then you probably know the typical benchmark consisting of ResNet 50 with TensorFlow on the ImageNet dataset. I call this the best and the worst GPU storage benchmark at the same time. Why I'll explain in a second. What we ran this on is the simple storage expansion concept, as I called it in the previous slide. So here we simply have a DGX1 with its 4 100 gigabit IB ports connected to a simple storage box with only 16 NVMe drives. Again, the box has 4 100 gigabit uplinks, so it's a 4-node 2U system here in this case. And let's see what we get out of that. So the good thing about ResNet 50, TensorFlow, and ImageNet is that it's easily comparable because all the vendors put out numbers for these results here. And there is the number published by NVIDIA. This is the maximum that can be achieved on the DGX1, about 8,000 images per second. And this is the highest published competitor result that I found on the internet. As you can see, it's using 48 NVMe drives compared to our 16 here, and runs on 8 servers. So much more hardware, but still not meeting the number that we easily got out of the single NVMesh box here by using this direct attached storage approach, just running a local file system. There's no parallel file system in between here, just making the volumes directly available, running XFS on top of that. And then it seems like it's internal storage to the box, and we're reaching the full number that's possible in the benchmark. So that's why it's a good benchmark, right? It's good to show in comparison to the competition. And it's easy to run. We didn't do any special tuning to get this result, just out of the box. But the bad thing, of course, is the file sizes and the amount of computation per input object in practice are very different, right? So it's just one example, but there are many examples that you could run. And since we're already reaching the maximum, the question is, can we maybe even go higher and just can't show it with this particular benchmark because we're bound by the actual GPU workload. So that's why we ran another benchmark here to really show the limits of what is possible with NVMesh direct attached storage. And for this, we used the same system, only 16 NVMe drives directly made available to the DGX box with XFS on top of it. And then we used MD test as a benchmark to simulate a workload where lots of small files need to be read per second. And then we see what the maximum is that we can get out of that. And then the results are really amazing. We start here with only 4 kilobyte file sizes. And when you compare this to the competition, you will notice that they tend to not really read 4 kilobyte files in such a setup. They will only read 4 kilobytes out of larger files instead of going through the full overhead of opening the actual small files and closing them and so on. So here 4K means we're really opening a 4K file, reading it and closing it afterwards. And then we end up at 1 million 4 kilobyte files per second that we can read. And we see that already at 64 kilobyte file sizes, we're close to saturating the 40 gigabytes per second of network bandwidth that are possible with the DGX1. So yeah, if you're any bit like me, then these results are just mind-blowing because they are so far away from anything else I have seen with a parallel file system so far. And of course, you can make this performance available to multiple DGX boxes. There's no problem with sharing the single box across multiple DGX boxes. And that's the end of my part. That was kind of our story. But now, of course, I would love to hear your story as well and see how we can solve your GPU storage problems. So as we speak, my colleague is about to share a link where you can register for a session so that we can continue the discussion. Thank you.
All right, thank you so much, Sven. Very interesting. And while we have our second poll up, which inquires about your storage infrastructure, I can tell you that a lot of you folks are here to learn, but we are seeing the majority of you guys that have GPU servers to have multiple GPU servers. So that is probably good news for Jackie and her team. While we are doing the next poll, Dr. Dimitrios, can you start sharing your screen because the floor is going to be yours after.
Thank you very much. Hi everyone, I'm Dimitrios, and yeah, just a small correction. I used to be in Barclays card. I'm in the CTO office currently, so I'm in Barclays group, and I'm going really to talk about fast storage and GPUs for AI. So my experience. And this is actually my view. So through my talk, I cannot endorse any technologies, as we understand. I'm talking on behalf of Barclays, but these are my views about fast storage as GPUs for AI. So my group is actually horizontal across the bank. So we are having very many AI use cases from very, very different business use cases. And usually the business use case that we have, and we apply AI to, are these ones. So we're talking about fraud detection, and fraud detection has to do with cash withdraw fraud, credit card fraud for card present or card not present, recommendation engines, so which products should be recommended to which customers, delinquency prediction, if customer becomes or is about to become delinquent, can we predict in order to send them an SMS or something. A customer complaint classification, which is a very active NLP currently field. So customers, actually initially the project was supposed to be a sentiment analysis, but usually customers, when they phone a contact center, is always negative. So it was actually customer complaint classification. The program was actually renamed in order to see customers for which products of Barclays they're actually complaining for. Document classification, so very many documents, particularly for Barclays Legal, that are ending up, need to have it some automated AI in order to send these documents to the appropriate people without doing the visual scan initially. Then for IB, quite a lot of projects around bond predictions, not around high frequency trading as such, but bond prediction on time scales of seconds. And then we have quite a lot of projects around image processing and sound processing, mainly images from cameras and sound directly in contact center level, directly working on the actual WAV files, sound files. So these are some of the use cases, and I can say that 80% of these use cases are currently in production. They are quite different because we are dealing with structured data. Structured data, customer complaints are semi-structured data because we have actual complaints from given customers in natural language, but at the same time, we have the customer profile, which is a very structured Excel CSV. Document classification, unstructured, image and sound, very different data sets, different type of data sets. The only common thing that all these data sets have are that we have very large volumes of data. So all of this, we are talking about very big data sets, hundreds of terabytes and sometimes petabytes of data. And the main actually thing that is happening across all financial institutions currently is that this type of data are usually stored into a Hadoop type of storage silo. So Hadoop is actually the silo where we store this data. And Hadoop is quite good for the thing that was invented, but it's not so performant currently for all our AI loads. So Hadoop is a very good and cheap type of storage, big data in very cheap infrastructure. And building frameworks on the top of Hadoop, I personally believe, because I present my personal views on this in my experience, adds a lot of bottlenecks because you try actually to do things with a type of storage that was not supposed to be doing. So what was Hadoop is the classical library that you walk in and you select a book and you go through. What we want here is something like Google Books, that you simply Google something and you find it directly. So this is how I see it in my views. Still, Hadoop plays a major role because the major file format where we store all this data. So what are the current paradigm? So this is a typical Hadoop cluster with 45 nodes. So we have here, yes, 3 times 15. And each of these has a typical 10 terabytes of storage. It can be even spinning disk or NVMe's, we don't care. Usually it's spinning disk currently. Each one of these, let's assume that has 48 CPUs. So in total, this entire thing, it's a pretty big wardrobe actually, has 2,160 processing units, which are available in a distributed fashion to do parallel processing, and half a petabyte of storage, this entire thing. So the current paradigm that exists is that if this is not enough, or if the system is not very performant, then usually what we do is we do this. We add more of these wardrobes. And more, when we buy more of these pizza boxes, so we end up with something like this. And so let's say 4,500 processing units and 1 petabyte of storage, which is okay. And if this is not enough, we end to something like this, which is the very common tactic in data centers. This is why the data centers of big companies, they have this type of format. The problem is, if you do an end-year analysis of, let's say, let's take this cluster here, and let's say that this belongs to a given business unit. If we do an end-year report and say, okay, this thing was used throughout the year, how much % of the CPUs was used for each server, you find an average of 5 to 10%. Despite the fact that the entire cluster is used throughout the year, each and every individual CPU is only used 5 to 10%. And the reason is that there are a big variety of workloads. There is a very big variety of business use cases. There is a very big variety of file types that people actually, and queries that people actually throw on this cluster. So everything is used, but with a very, very low actual CPU usage. So let's take again this and let's see where we can go actually. We have this with 2,160 again processing units of 450 terabytes of storage. And then we have this. So let's take only the upper two parts and split them into a compute server with GPUs, exactly the example that Sven showed before, and a storage server. So this in your data center will occupy this part here, only this thing. So 4 use each, so let's say 8 use, something like this. So you see here the unit, so 4 use altogether. This is the GPUs, a server, a custom-made server, or a DGX1 that has NVIDIA GPUs in, all the good stuff. And this is an NVMe server, which is simply a storage server that you go and you plug on the back part NVMe's. Here we have on this server 5 NVMe's, 1, 2, 3, 4, 5. You can go up to 30 NVMe's per server. So assuming that the NVMe's are around 10 to 11 terabytes each, sorry, yes, first of all, let's go to the GPU. So the total processing units of this part here is 2,160. With 4 GPU cards here, we have 20,500 processing units. Only on a single server like this. This is the actual processing power. This is the CPU processing power. This is the GPU processing power. With respect to storage, let's say that we have 28 of these NVMe's, each one going up to 20 terabytes. So we can have on a single storage server up to 560 terabytes. And actually, this is quite customizable because I don't want really to fill it up all. And it's a big advantage if you have a software-defined NVMe, a software-defined storage layer. Because, initially I would never go and buy 560 terabytes of storage, not even 100 terabytes of storage. I'll start with 20, 30, 40. And if I have the business use cases, I'll be populating this with more NVMe's. And there you are. So I need at this point a very flexible way to adjust my storage based on my business needs, and also not to be locked on a hardware, which is here, a hardware-defined storage that is fixed. And the only way to scale it out is either to add more of this or to take it out and bring a new one. So this is a big advantage of software-defined storage because it's very customizable. And even assume that all these were NVMe's, I could really take different cards from NVMe's and populate different servers and actually have the same NVMe cards for use cases that require more storage than others. So this is a very big flexibility of software-defined low latency storage. So these are some, of course, not Barclays figures, the costs that you can find on actual, on the web. So the total cost of such a server is around 2 million. This is the hardware cost. And then you go with software, proprietary software that some companies are using, and power data center footprint, how much energy this thing is consuming. So assuming that each and every rack consumes around 15 to 20 kilowatts of energy, this is quite a big energy consumption per year. And these are the lock-in costs. So whatever you need in order to make all these things work together. And these are, of course, all the distribution layers. It can be a proprietary Spark version and so on. So in total, such clusters, we are talking about millions to maintain, which are quite big clusters, but you are talking about this type of figures. Plus, everything that you need to have to run here has to be distributed and multi-node, which is a mandatory requirement. However, if you have the single server that I showed you before, single GPU server with single storage, you have only the price of these things, which is actually the 4 GPU server, the 5 GPU server, the DGX1, and the actual storage. But then you can use open source technologies. And if you really want to isolate it in a silo mode, so each and every business use case has its own server without be connecting due to data privacy and so on, then one of these servers can perform very heavy workloads. So you cannot even need to have even neither non-distributed frameworks. You can use all open source Python, R, whatever you want, and you can run your codes directly on the GPUs. So this is a dramatic cost reduction. And at this point, you have to say that we have a 90% cost reduction based on public figures about these two, and we have 5 times more compute. So this is 2,000 compute cores, and this goes up to 20,000 compute cores. And it can go up to 60,000 compute cores if we have a DGX1. So this is exactly currently a very big business value from a cost perspective, even if the AI models are not so good, but they are good. So we have even more cost reductions. So another thing that I would like here to mention is that everything on this part depends on how fast is your storage, and secondly, on how well, because we rely here on NVIDIA GPUs. So in effect, we rely on how good actually the underlying CUDA libraries and so on are robust. So currently with the CUDA version, so the latest CUDA version, CUDA 10 and so on, we have very, very, very robust frameworks, at least around TensorFlow and at least around GBM type models such as XGBoost and LightGBM, that we can produce very fast production ready models using this layout. For libraries, and this is exactly what also R&D, what I'm currently doing, we are very keen on actually on this layout having more traditional AI algorithms such as random forest and K-means, the traditional AI, to be able to run on GPUs. For this, NVIDIA has Rapids, which is a big new framework, and we are actually really investing some time to see what we can do with Rapids in order to move completely away from all the Spark type libraries that exist on these big gigantic clusters. It's then referred to one advantage of having software-defined block storage with low latency, which is we leave intact the CPU. Now, and we said that we overpass the CPU, so this is faster, which is of course of great value. But there is one more thing here that I would like to add, which is pure from an AI perspective, and this really makes a big difference. We talk about GPUs, and GPUs, that's fine. Yeah, so somebody in this context, somebody would ask, so why we need to overcome, why we care about the CPUs? Even if I use 50% of the CPU, why I should care? These are not playing any part during the model training and so on. This is actually wrong because CPUs still play a central role in all AI. So here you see a very mainstream life cycle of a machine learning model. So here you have your variables, and variables are the model variables. These are the TensorFlow variables that you want after the training to have a given set of values. So in a normal layout, so what you do is you have the variables and you have your model, and you distribute this model on the GPUs. So during the model training, GPUs are doing one and only thing. During the model training, GPUs estimate the gradients. So gradients are actually, if we have a minimum, they locate the best route to go to this minimum. And this is what GPUs do. So if you have multiple GPUs, at the end of each round, epoch, as we call it, all these gradients need to be averaged. And this is where CPUs come. So during the entire epoch, so during the entire training epoch, a single training epoch, the life cycle is data populate the graph which lives here. Variables are updated during this cycle, during the gradients. And for each and every round, the gradients which are spit out from the various GPUs are averaged on a CPU. So GPUs are quite fast and their throughputs is quite high. So we are talking about the DGX1 throughputs 25 to 30 gigabytes per second. So, and this is continuous. So we need to have as much as CPU available in order to estimate the averages, update the weights, and continue. If this is not done, if one of the GPUs is not able to pass data to the actual CPUs, then the entire process stops and we wait all the GPUs to be able to load data to the CPUs. So CPUs are quite important. Therefore, it's very important to have all available CPU. Moreover, and I think I'll be stopping here for my conclusions, what I would like to say is that another advantage of software-defined storage, actually, low latency storage, is that if I go to this paradigm before, is that hardware storage tends to be from a price point not only quite pricey, but it's quite difficult to start convincing people that, okay, I would like a hardware storage that has more memory than my normal storage. It has FPGAs in, it has a completely new infrastructure. And people are going to say, okay, I can understand in so many years we're selling the fact that, okay, initially we had this compute and it was only to do SQL. Now we have this compute using actually the CPU to do AI. So this is not good enough. We now use this to have GPUs, graphics card, and I understand the cost. And then we have FPGAs on the top. We can have ASICs to bring the programming really on the chips and so on. So this cost, because it's computer, can be actually, you can somehow say why you need them, but storage is storage. So it's very difficult to sell to a stakeholder that I would like my storage to have FPGAs, memories, and so on, because then the storage, actually, the hardware storage has all the components to be more performant than your actual compute storage. And this can create within a regulated environment quite a lot of problems. Another advantage of having software-defined software is that it can be fully maintained by the actual infrastructure people that you already have. Hardware-defined storage for big institutions is an appliance because it comes with pre-configured hardware and software specifications. If something occurs, the support of this is quite cumbersome and quite costly as well. Having a software-defined infrastructure, you can play as an infrastructure guy that works in an organization this, and then you can reconfigure on the fly the NVMe's that you have based on your business without involving, without going back to the company. So you can support this internally. My conclusions are going to be the following. We talk about accurate and precise AI models, and these are usually involved with deep neural networks and so use. and so on, these are usually very complex and very lengthy. And lengthy mean that they are very big. So the actual code is very big, and this is what makes them complex. So complex and lengthy AI models require big data in order to be trained, because the more parameters, the more the data. We have both. So we have both complex model and we have big data. So this, we need, for these two, we need fast GPUs. And I think NVIDIA is doing a very, very, very good here, plays a very important role, because the GPUs of NVIDIA are quite fast currently. So this is also ticked. But if you have fast GPUs, that they are not hydrating very fast with data, then why to have them in the very first place? So data hydration is the most important thing in order to make the most out of GPUs. You might have a GPU that is standing there and you have only 15 and 60 and 20% usage due to the fact that the data are not very fast hydrating your GPUs. So fast data hydration with minimum CPUs, because CPUs are also needed, can be achieved, and we have found out that it can be achieved by software-defined block storage. So, and this is where I'll be ending. That's it.
All right, thank you so much, Dr. Dimitrios. Great presentation. And before we go to the questions, I wanted to launch the last polling question and let you guys know that from those folks that are using storage for GPUs, the majority are using NVMe appliances, followed by all-flash arrays, and then a few are very happy with just the GPU storage, the internal GPU storage. And then the last question that we have for you guys to answer is which performance requirements do your GPU workloads have, whether it's rather high bandwidth or IOPS or low latency or all of them. Just take a few seconds to answer those, and then we will switch to Q&A just for a few more minutes. And while we do that, I would like to take the opportunity also to promote our next webinar, which is on May the 4th, where our CTO, Yaniv Rumem, will be talking about technology roadmap, what's coming next essentially from Excelero. Is going to be very exciting. Someone's posting the link, but it's a fairly easy link to subscribe, excelero.com/roadmap to subscribe for this webinar. All right, and then to the questions, there was a whole lot of them. We're at the top of the hour. We'll see how many people have to drop, but I wanted to take the opportunity to still ask a few questions. The shortest question, maybe for Dr. Dimitrios, if you can, is Roger was asking what your read-write mix is for your applications.
So you need the IOPS. Is this what you want to tell me?
I think the question is mostly whether you have whether your applications are heavy on the read, heavy on the write, or whether it's both of it.
It is both. It is both. I cannot share any number, but it is both.
Okay, great.
Yeah.
And then David was asking, I'm going to shorten the question. He liked your cost comparison, and he was asking whether you had also looked at cloud-based services for that, and whether you know how it compares to those solutions.
Yes, so yeah, from an R&D perspective, currently I cannot share the figures, but I'm doing a full reproduction of the same environment on cloud and see what are the cost benefits. One thing is for sure currently, if somebody is really interested about how performance computing, and we are talking about even beyond AI and going towards, let's say, high frequency trading and so on, currently, based on the numbers that I have seen for our benchmark, is quite difficult to achieve currently.
Okay, thank you so much. And then I want to share a question for everybody. Yeah, I think this one is going to be a perfect one for Jackie. It was Andre who was asking whether Magnum IO as a software stack, whether it's already included in the CUDA releases and whether it requires separate licensing.
Well, Magnum IO, hopefully, can you hear me all right, Tom?
Yes, yes.
Magnum IO is currently available, and GPUDirect Storage as a part of that is in beta stage. And so we have the suite of products that I talked about that are available today with Magnum IO and CUDA. And then our GPUDirect Storage will be integrated into CUDA at the time of our production release, which is coming fairly soon here this year.
Okay, perfect, great. And then just one more question, because I want to be conscious of everybody's time, but I think this one was really interesting from Niraj, if I'm pronouncing that correctly. And so this one is for Sven. Niraj was asking how to avoid parallel file system, but still allow reads and writes from multiple DGX servers to external NVMe storage. Sven, can you share light?
Yes, yes. So this makes mostly sense, of course, for the training phase of the deep learning, where the major part of the performance is needed for read-only datasets. Of course, these datasets can grow over time, but the actual workload is running on the read-only training dataset. So that's how it's possible to use a local file system as opposed to a network shared file system, and make that local file system read-only available to any number of GPU servers. Typically, we then hear, okay, that's no problem because the small amount of model updates that needs to be done can simply be done to the internal storage, or the write requirements for that are so low that it's easy to set up NFS server, for instance, on any of the boxes to have the shared write space as well.
Okay, thank you so much, Sven. Sven, Jackie, Dr. Dimitrios, thank you so much for your great presentations. To the audience, thank you so much for being with us, so many of you, and for the entire hour. It's really amazing. I think it helps that we can go to real events, and for that we're doing our best to still all stay connected and transfer the information to you guys so that we can help you with your daily challenges. I hope you found it interesting. I hope to see you guys on our next webinar, which is already in 2 weeks. Thank you again to my panelists, and stay safe, stay healthy, keep a distance.